Hi, I'm Wim Bogaerts from Ghent University and IMEC, and today I will talk to you about programmable photonic circuits as a flexible way to make manipulations of light on a chip. Now, if we think about programmable and photonics, the two first words in our title, we think about things that we can manipulate in software, things that can be changed by just changing lines of code. While with photonics, we think about manipulating light on microscopic scales. So if we bring the two of them together with programmable photonics, we essentially manipulate light in software on a microscopic scale. And why would we want to do that? Well, because light contains information. Now, if we manipulate light in a traditional way, we typically think about using optical elements like lenses, mirrors, polarizers. And if you want to do that in software, we have to go to spatial light modulators, for instance, where we can control light with pixels. But this still doesn't scale very well. Look at this optical table. So the trick is, if you want to manipulate light on a very granular scale, you have to go to chip scale. Just like with electronics, when you start integrating photonics on a chip, you get a lot of benefits in terms of performance, power consumption, footprint, and cost. Now, one technology to make photonic integrated circuits is silicon photonics, and it has the key benefit of being able to do really high density photonic integrated circuits, and moreover, it can be done with the manufacturing infrastructure that you also find in CMOS electronics. So essentially you get two scaling benefits out of the silicon photonics. You get the large scale manufacturing and you get the submicron scale waveguides, which allow you to do really large complex circuits. And this brings us to this particular graph, where you see the number of components integrated on photonic chips over the years, and you see a kind of Moore's law, where you double the number of components on a photonic circuit, like every 12 to 18 months. Now, one thing that you have to take into account in this graph is that all of these chips are ASICs or ASPICs. They're application-specific photonic integrated circuits. They have been made for one specific purpose. Now, to realize what the impact is in this story, let's go to one example. Let's say we want to build an optical transceiver for a data center. Now, to build this, we first select a protocol, and then, based on that protocol, we design, fabricate, package, and test the chip. Let's say, for instance, we want to go for parallel single mode fiber. That means that we need 4 upstream fibers, 4 downstream fibers, and so the transmitter needs 4 modulators, and the receiver needs 4 detectors, and they need to be wired up on the photonic chip to the respective fibers. Now, if at some point you want to change protocol and go, for instance, into coherent communication, you have to start all over again. Essentially taking the same type of modulators, the same type of detectors, but organizing them in a different circuit on your chip. And if you want to do, for instance, wavelength division multiplexing, you're going back to the same problem. You have to design a new chip, again using the same type of modulators and the same type of detectors. Now that's quite costly because it can easily take you a year to design and fabricate and test a new chip, and a kind of $500,000 to $1 million. So that's very costly if you want to be quick to the market and you want to have a reliable product. In electronics, this is typically approached in a slightly different way. If you want to prototype a new idea or a new functionality, you get an off-the-shelf programmable photonic circuit, off-the-shelf electronic circuit, like a field programmable gate array or digital signal processor. And you have that within a day, and then you can start programming and testing, and maybe within a month you can already check your value proposition and your functionality with a customer. And only then, if it's really needed, you design an ASIC to make it more efficient. Now, an FPGA essentially consists of logic blocks which are connected with programmable interconnects. So where are the photonic equivalents of these FPGAs? Now, I want to coin a very specific definition here. What I mean here with a programmable photonic circuit, to be really equivalent to an FPGA, it has to be a circuit that can be reconfigured in software to perform different types of functions. So it has to be sufficiently general purpose to be able to be useful in multiple functions. Now, a programmable chip would look a bit like this. A black box, where you have optical signals going in and out, and the box processes the signals, but not just optical signals, also high-speed electrical signals, radio frequency signals. Now, if you look at that in a bit more detail, the optical interfaces are, for instance, an optical fiber array. But for the high-speed interfaces, the high-speed electrical interfaces, essentially the electrical signals coming in from the right here in this picture would immediately be translated into optical signals by phase modulators. And at the output, the optical signals would then be converted again into RF signals. Now, the center of such a chip is a programmable all-to-all scatter matrix, essentially coupling all the ports, input and output ports, together in an arbitrary way, so you can do it in a kind of linear combination. It's not just digital switching, it's really an analog redistribution, both in amplitude and phase. Now this is quite complex, so let's simplify this a little bit, and let's assume that we now have a set of inputs and a set of outputs, and light only travels from left to right to the circuit. Now if you have no reflection in this system and no losses, this transmission matrix would be a unitary matrix. Now, the first idea of how to implement that was already coined in the 90s, but it's only in the past 5 years that technology has been really coming of age to allow us to make these circuits. And so what you need to implement such a transmission matrix is a network of unitary 2x2 gates. These essentially are tunable couplers and phase shifters. That's the only components you need here. So if you organize them in, for instance, this triangular shape, you can construct any linear combination of inputs at the outputs. The first demonstration of this was done in 2015 by University of Bristol in a low contrast material system, and 1 year later in Ghent we did something similar in silicon photonics in a high contrast system. And then again 1 year later we saw this already massive chip with 26 inputs and outputs coming out of MIT. Now, why would you want to do this kind of this function? Essentially, you have your light propagating from left to right. Well, essentially, this circuit can perform in real time a matrix vector product. Your input amplitudes, amplitude and phase, and your output amplitude and phase represent a vector, and then your circuit in the middle actually is the matrix that performs a matrix vector product, and basically mapping all your inputs onto a linear combination of outputs. Now, these functions, such as a multiply accumulate operation or a matrix vector product, can be useful for a number of applications. For instance, just quantum optics. If you send single photons through such a circuit, you now get a situation where you can perform linear quantum optic operations on these single photons. You can mix them together and you can get hybrid states. Another area where you can use these circuits is in machine learning or neural networks. Multiply accumulate operations are very, very useful for these systems to mix the neurons together. So it's not surprising, for instance, that one of the first real applications of this type of circuit is in artificial intelligence. And only last month we saw an announcement by the Boston startup Lightmatter of their 64 by 64 matrix multiplier chip. Now, one thing to keep in mind with all of these circuits is our definition we put up earlier. These are programmable circuits, but they're not necessarily general purpose. The left to right architecture essentially limits what you can do with such a circuit. To make it really general purpose, you do need an all-to-all scatter matrix. And to implement that using these unitary gates, you need to organize them in loops instead of a forward-only network. So you get these recirculating square or hexagonal rings. Now, the hexagonal architecture is the most flexible because it really allows you to use every port as either an input or an output. Now, in such a mesh, you can now route light just by reconfiguring your couplers from cross to bar state. And you can even route it back onto itself. You could even route it back to the original port in a loop. You can do multiple routes at the same time, nothing is stopping you, and you can even route light through the same coupler. And that also makes it easy to make a crossing, which is usually hard in a traditional photonic circuit, because you just have to switch your coupler from bar to cross state. The couplers don't necessarily need to be in bar and cross, they can actually be also in a partial state, so you can use them as splitters and power distribution networks, or when you combine them again, you can make interferometers. And you can, because you can implement delay lines in the mesh as well, you can make filters. So you can adjust the delay per unit length. You can also make ring resonators by guiding your light in a loop. The first implementation of such a circuit was done by the Polytechnical University of Valencia, where they made a 7-cell hexagonal mesh in the Kapmani group. Now this can already perform like 100 different circuits. For instance, you can make it into a double Mach-Zehnder interferometer, where you split the light up and combine it again and split it up and combine it again. Or you can make this other type of filter here behind me, where you can route light again through multiple paths. And because every coupling and phase is tunable in this circuit, you can control the shape of the filter response. You can also make resonant filters like this ring resonator here, which can also again be tuned in terms of quality factor and extinction ratio. Now this is a 7-cell mesh. If you really want to make large-scale programmable circuits, you need to be able to scale this up to a much larger circuit. Now, what do you need to do that? Well, you need only 2 types of components, the 2x2 unitary gates. But they need to be compact, they need to be low loss, have a short optical length, and low electrical power. And you don't need just good ones, you need a lot of them. So that means that you need to bring in the electrical signals, you need to control electronics to govern whatever is going on the photonic chip. Again, as a reminder, you need phase shifters and tunable couplers for that. And what is the easiest way to make them in photonics? Well, it's a very simple Mach-Zehnder interferometer. You have a splitter, you have 2 phase shifters and a combiner. And that allows you to control the tunable coupling and the phase shift. The easiest way to make these phase shifters is heaters. So in silicon photonics, heaters are the classical way to implement these devices. However, they have a big drawback. Essentially, they're generating heat, so they're burning power, and eventually that will also lead to thermal crosstalk. So to scale this up, you really need better phase shifters and tunable couplers. And one particular implementation, for instance, is the use of MEMS, micro-electromechanical systems, where you bring, for instance, in this case from EPFL in Switzerland, you have a tunable directional coupler, where you can move one of the 2 waveguides of a directional coupler down to control the coupling from fully 100% to 0. Likewise, this is an example from KTH in Sweden. You can have a phase shifter where you have a thin silicon beam close to the waveguide, but you can pull it away with a cone drive actuator. Again, this is a very powerful effect because you're essentially moving high contrast material around. Now, these phase shifters are only a part. I mean, you can build a large circuit with such phase shifters, but then you need to control everything. So you need a lot of layers on top of that. You need the analog electronics for the driving, you need digital electronics for control, and then you need software layers to implement the functionality you want. So all of this has to come together. And the first challenge there is the packaging. I mean, you need to have the driver electronics close to the photonic integrated circuit, you have to have fiber attachment, and most difficult of all in the packaging challenge is actually bringing these high-speed electrical signals in and out. This is kind of challenging, and it's usually a costly aspect of the photonic circuit. On top of that, apart from the physical interfaces, you also need the software layers on top of that. So you need the logical controller close by with feedback loops that make sure that all the actuators stay on their set position. You need configuration algorithms to figure out how they should be configured, and higher level synthesis algorithms to basically define functionality and place them inside the mesh. On top of that, you need a layer that helps you design. So you basically, when you buy a chip like that, you also get a development kit. Now, essentially, that gives you a completely new way to design photonic circuits. Where in the past you used full custom design by essentially drawing geometries, and now it's becoming more fashionable to use standard PDK components and click them together in a circuit. With a programmable photonics chip, you actually already have the circuit. It's a matter of configuring which couplers you're going to use and in which state they need to be. And essentially, this translates your design into code. Now, this programmable photonics can lead to new types of design IP. Just like in programmable electronics, you can think about routines that translate a circuit schematic into the necessary functionality that can then be programmed and synthesized inside one of these programmable photonics. You can think about new control strategies and new algorithms that can run on the electronic control chips. And finally, you can use these programmable blocks and put them and use them as a part of a programmable, still application-specific circuit. So all of these models do not yet exist in photonics, but they're quite common in electronic design. For instance, some of these programming algorithms could be based on graphs. This is some work that we've been doing in Ghent in our group. We've been devising a model, a graph-based model, to represent these photonic circuits and still respect all the physical constraints that you have in these circuits. For instance, that light cannot flow back, that light cannot just change direction from in one direction to the other. As a result, we can actually now configure these circuits quite efficiently. So this is, for instance, a routing problem where we wanted to route multiple routes at the same time without collisions. And so our graph algorithm can do all of that and negotiate congestion in some of the nodes. This is a distribution problem. So again, we have different forms of congestion here. In the left figure, we're trying to route with a minimum of components, while in the right figure we try to minimize the power which is in each of the waveguides, for instance, to reduce nonlinear absorption losses. These algorithms can present a bit of a problem, of course, because when you configure those, you don't necessarily know that all the couplers are exactly in the state that you want them. For instance, there could be slight deviations in the coupling. And as a result, you get leakage paths, you get parasitic paths in your circuit, which can actually, because everything is a loop, it could be a ring resonator. So what you get, even with 1% random variations on the nominal coupling values, you can still see these resonances in the transmission spectrum. And that's not something you want. Now, you can try to compensate that in hardware, but you can also come up with algorithms that help you configure these circuits and get rid of these resonances. For instance, if you just set all the unused couplers in a cross state, you're shunting away all the light from these resonances to the edge of the chip. And as a result, the resonances all but disappear. You still get some loss, but you don't get these spikes anymore. Now, essentially, if you bring that all together, you have an entire technology stack, starting from the photonic chip all the way up to the programming algorithms and the software interfaces. So this processor, which now looks like this, has a waveguide mesh in the center. And everything else, the signals and that, can be configured. If we go back to our example now, we can take our parallel single mode fiber architecture and just route all the modulators to the right fibers and all the input fibers to the detectors. But we can just as well reconfigure the circuit to reroute the transmitter signal to an IQ modulator and implement a 90-degree hybrid for the receiver. Or we can make use of the fact that we can program filters inside our mesh and do a wavelength multiplexer and demultiplexer on the chip. We can even go beyond transceivers. You can easily imagine that you can just reconfigure this circuit as a switch matrix, mapping inputs to outputs just directly. You can use it as a beamformer circuit, because all these elements are also phase sensitive, and you can even use the fast phase modulators for rapid beam scanning. Or you can use it to process microwaves using your modulators as RF inputs and your photodetectors as RF outputs, and essentially use the mesh to program filters to filter these RF signals that are modulated on your laser. All these chips could be used in principle in a lot of applications because of their flexibility. So you can use them as fiber to the home subscription modules. You could even use the RF functionality, for instance, to implement an XDSL over fiber link, or use the RF functionality for radio over fiber for 5G antennas. You can use them as sensor systems. For instance, readout for fiber Bragg rating sensors in a building or in constructions. You can use them as a hub for multi-sensor readouts in automotive, or even as the engines in a frequency modulated LiDAR system. Now, you can also use them in biomedical sensors, like for blood analysis, readout systems, or optical coherence tomography. And finally, some other examples. These matrix manipulations could also be used for optical hashing functions, blockchain calculations, or even for quantum key distribution. So there's a whole lot of applications where you could apply these circuits to. So this does make this circuit one chip to rule them all. It can handle many functions. It's very flexible, but it's also a large circuit, so it will have higher loss and it will be more expensive than an application-specific circuit. So does it make sense to use these? Well, let's have a look at the costs here. If you make a photonic chip, you essentially have to make the photonic chip and the electronic driver chips. And essentially, when they arrive at your doorstep, you then have to do the packaging, assembly, and testing. In the case of an ASIC or an ASPIC, all the costs belong, or all the costs end up with the consumer or the customer who's making the products out of these chips. However, if you take the situation of a general purpose photonic chip, we can now imagine that there will be a chipset supplier who is delivering these chips to multiple customers. So this chipset supplier, who obviously needs to make a bit of a profit, can still divide the costs for all this wafer scale production over many customers. So that's a major cost share. So let's do some calculations here. Where are the costs? Well, we have the costs in the silicon photonics chip and the driver electronics, but we also have quite some costs in the packaging. And for all of these costs, there's an upfront development cost, but there's also a cost per part. For the wafer scale, let's assume that we use kind of generic 200mm fab, so we put in some numbers which are typical for 200mm fabs, both for the photonics and the electronics. And then for the packaging, we take a cost which is mostly dominated by the fiber connection and the RF connection cost. So, with these costs taken into account, we use three scenarios. One where we have no RF connection, so a cheap version of the chip, a somewhat more expensive version which has 4 RF connections in and 4 out, and then a high-end photonic chip which has 32 fiber ports and 16 RF input and output connections. And for each of these, we calculate, we put a number on the design, fabrication, package, and testing development. Now, obviously, because a general purpose photonic integrated circuit is much larger than an ASPIC, it will be more expensive. It's larger, it takes longer time to design, package development is more expensive, etc. Now, the cost model for an application-specific circuit is quite simple. You have the non-recurrent, one-time engineering cost, and then you have a proportional cost per chip. We make it a bit more complicated, taking into account that the chips are fabricated in lots of wafers, but overall, this model will hold. So that means that if we plot this on a graph as function of volume, we get this inversely proportional curve, where the cost per chip decreases as we have more chips. Now, for a programmable chip, a general purpose chip, this model is very similar, except that the cost for the customer is now only proportional to the number of chips, to the number of chips in the order rather than to the total number of chips. So you now get a cost per order which can be significantly lower because the non-recurrent engineering cost is divided over many more users. Of course, you have to take into account a profit margin for a supplier, which we here count at 30%. So if we plot these two together, of course we see that for a given volume of fabricated chips, the programmable photonics chip is more expensive. However, we have to compare the chip for the programmable photonics with those fabricated at a higher volume, in this case, let's say 100,000 units. And we see that at that point, the cost for the programmable chip drops dramatically compared to the cost for an ASPIC at lower volumes. And that's where the difference is. So if you want to develop a product either in prototyping phase or at low volume phase, a programmable chip could actually make a big difference. And we see that indeed in all of the three scenarios for lower volumes, we get a significantly lower cost per chip, a cost for the total development than we get with an application-specific chip. And that's not counting another key advantage. You have a much shorter development time. Essentially, if you have a supply chain from wafer scale fabrication all the way to your product, you're essentially cutting your development in two. While all the work that leads to the fabrication of your programmable photonic chip is cut out and is reduced to a few days lead time and a slight learning curve to learn how to program it. So that brings me to the end of my talk. Programmable photonics can really make photonic circuits smarter, in the sense that you get a more upgradable, more flexibility. And the advantage is similar as with programmable electronics. It really lowers the adoption threshold. So you can go to faster prototyping, you have more people using photonic circuits, and you can get a lower cost for low volume specialty products, so a lot more market opportunities. Now, the challenges are still out there. These chips do not yet exist, except in like first experiments. So we still need to get the losses of the couplers and the phase shifters down. We need to get the entire technology stack worked out, control electronics packaging, programming algorithms up to the development kits. So that's quite a lot of work to do. That's also what we're working on in our group in Ghent. So I would like to acknowledge my entire team who generated quite some of the results that I presented here. And also want to acknowledge the European projects Photonic Swarm and Morphic. Thank you.